Okay, good morning. So, do you remember we talked about some formulas? This was the formula I told you that this is also another deviation from uh, number algebra, that if you have matrices, square matrices of the same order, there is no guarantee that this formula is true unless you know that A and B commute, okay? Unless, so let me just take it over, not true in general. But true if A and B commute. And then we also talked about, is it possible to have algebraic identities when it comes to matrices? And then we realize that the answer is no. For example, there is no guarantee, assuming that A and B are square matrices of the same order, there is no guarantee that this is equal to this matrix. Okay? Again, not true in general, but true if A and B commute. So algebraic identities, you can use them if you know they commute. For example, there is an algebraic identity, might be it's not very familiar to your eyes, but this is very easy to establish. And this one is the square of a trinomial. So you already know the square of a binomial. Square of a trinomial is also similarly can be deducted. So this becomes a squared plus b squared plus c squared plus 2 times the first times the second one plus 2 times the first one times the third one, and finally plus 2 times the second one multiplied by the third. So that is also an algebraic identity. So if A, B, and C are numbers, this is always true. But now assume that I have A, B, and C matrices. Okay? When do you think this might be true? So if I want to write the same thing for matrices, A, B, and C are matrices of the same order, square matrices of the same order, if I want to use this, first I have to check commutativities of involved matrices. So for this one, I need to check the commutativity of A and B. I need to check the commutativity of A and C. And I also need to check the commutativity of B and C. If all of them are commuting pair of matrices, then I am allowed to use this identity. So that is the core of last time lesson, yes? Is that clear? So if you want to use this formula, you have to be sure that you have to make sure exactly the same thing here. If you want to use this, ABC to power 2 equals to A squared, B squared, C squared, you have to make sure that any pair of them commute. A with B, A with C, B with C. Okay, so if you want to use them, first you have to convince yourself that every pair that are appearing there is commuting, then of course you can use them. It's not a good way to write these things, so I hope that you hear me that these are not in general true, yes? Not in general true. For this one, for that one, for this one, for that one. Yes. Okay. So that was the core of the lesson last time, but then we didn't have time to finalize these 3 examples. So I don't know, have you thought about this or not, but that's a good idea if you give you time to think about these problems now, okay? Let us just do them one by one, okay? Let us focus on problem, on example 124. Let a squared be equal to 2 times a minus 3i. So we don't know about the order. So there is no way for me to understand what matrix A is to compute it. What I know is that there is a matrix A whose second power is 2 times itself minus 3 times the identity matrix. We want to show that under this condition, the fifth power of that matrix is 12 times the identity matrix I minus 11 times matrix A. So these kinds of questions are interesting questions when it comes to matrices. So I will pause recording and wait for you for, I don't know, 5 minutes probably, and then I will ask your opinion about it. Okay. Okay, so 5 minutes is now past. What do you have any idea about the first example that I have written here on the board? So we know this. We want to prove if this is true, that is also true. Do you have any idea where to start? Yes?
Could we try expressing simply what A is equal to? So if we try to remove the 2 by multiplying with 1/2, and then we get the 3i to the other side, we know what A is. Then we
No, we don't know what A is. Then
well, we
A
can
will
know
be
it
written in terms of
the
A
other
squared.
side. We can know it in terms of the left-hand side.
But the left-hand side is also involved with A.
Yeah, but what I'm saying is if we can get what
So let us,
is,
okay,
then
might be.
we square
So
it
what
to
you are
5.
saying is that I multiply it by 1/2. Let me see if I'm recording. I can take this. Yes. So you say that I multiply by 1/2. Okay. So then it becomes A,
Yes.
and then it becomes 3/2 I.
Then we get I to the other side. And
This one to the other side. So 1 over 2A squared minus plus 3 over 2I is equal to A.
And now if we a to the power of 5 would be that expression to the power of 5, and I think that a squared and the identity matrix commute, so we can expand it. Right?
Yes, you are right. If I raise it to power 5, I can take the whole thing to power 5, and because this part and that part are commuting, because A and commute, but I don't think it is hopeful that I can get to the answer.
Maybe not, but
Because if I raise it to power 5, no, you don't need to do that, because when you raise it to power 5, of course, first of all, you need to know what is the formula for the fifth power. Let us put this aside, assume that you know that. But still, this one will go to power 5. It becomes a to power 10. It means that you prove something which is true. Of course, that is true. When this is true, you raise it to power 5, you get something, definitely that one is also true. But it is not that hard to see this will not be what I want. So this, if I am you, I will not actually spend time on it. Is that clear? Definitely I will get an equality which is true, but it is not hard to see that this will not be that one. Yes. And beside that, I will not give you so computationally complicated question if it is not that interesting. Yes.
Do we need to prove that A commutes? Is commuting with A?
No, I always commutes with L. Any matrix commutes with I.
Okay, we don't need to show that A equals A squared.
No, we don't know. How do you know that A is equal to A squared?
No, like you can figure out that A squared A to the power of 5 is equal to that answer.
Yeah, we want to find that. We don't know
only
yet.
if you use A squared equals to A minus 3i. But
yes.
I think that only works if A is equal to A squared.
No.
Okay.
But you see A is not equal to A squared. So if A is equal to A squared, so instead of A squared I can put A, and then it means that A is 3i. But if they haven't given us that A is 3i.
Well, okay, either way, I can help you get the answer then.
No, but you cannot use that, that's what I'm saying.
Cannot you? No, but can I use A squared equals 2A minus 3i?
2A minus 3i.
Yeah, okay.
Yes.
Well, I did that.
Okay.
So you can write A to the power of 5 as A squared times A squared times A.
Exactly, that's good. So let us just start. So what you are saying that, let me start from here. So the left-hand side of what I want to prove side is, but I just want to do some small rectification. How do you say it in English? Small changes. So I would write it as A to power 2 to the power 2 and then multiplied by a. You told me a squared times a, which is true, but if you don't mind, let me write that one. That's also true. Okay, then
you switch the a squared for
with
the
that
2a.
one given.
Yeah.
Yes, that's correct. So instead of this a squared, I can use my assumption. A squared is given to be 2i minus 3i, and then to the power of 2. And there is another a coming in. Yes? Now, in your method, you started multiplying probably things, which is true, but can I use algebraic identities here? That is possible, because 2a and 3i commute. Yes, 2a times 3i, the answer is 6a times I, which is a. 3i times 2a, which is 3 times 2, which is 6 again, but I times a is also a. So it doesn't matter for this particular case, it doesn't matter in which order I multiply them. The answers are the same. So this means that these two matrices commute. So if I want, I can use algebraic identities as before here as well. The counterpart of algebraic identities here. So this becomes the first one squared, which gives me 4a squared. 2 times the first one times the second one, I can do it in my head. So it becomes minus 12. A times I, which is a. And the second one to power 2, which becomes positive 9, I squared. But I squared is I. Yes? And then multiplied by a. I think you should also have got the same result, but by multiplication and simplification. Okay, so then how should I continue?
You switch the a squared
Again. So whenever a squared appears, so I switch it with that expression. So then it becomes 4. Instead of a squared, I plug 2a minus 3i. And then I have minus 12a plus 9i. And then I have multiplication by a at the end. I do just simplifications here a little bit. So this becomes 8a minus 12i. And then I have minus 12a plus 9i multiplied by a. Simplification still continues, so this becomes 8a minus 12a is minus 4a. Minus 12i plus 9i becomes negative 3i. And then multiply it by a. Then what?
Multiply in the a.
Exactly. So this becomes minus 4a squared minus 3i times a is the same as a. Again, the story is to replace this final a squared with what is given, yes? So what I do, it becomes minus 4. Instead of a squared, I plug exactly the same thing, 2a minus 3i, and then I have a minus 3a. So if I have done everything correctly, this should be my answer. So let's just simplify that. So it becomes minus 8a, and then plus 12i, and then I have minus 3a. And then you see that 12i is just 12i, minus 8a minus 3a is minus 11a. And that is exactly the right answer. Yes? So these questions in matrix theory is also nice because you see you are using the rules of matrices, algebra of matrices. So you have to be careful about the algebra that you are using. You are using it in a wise way. So these are different from just normal calculations with matrices. So it is also important to know about this. So any questions here? Okay. So I wait a little bit more for you. I mean, so here I want to also, I forgot to put the question mark. So I want to simplify that in that question as much as possible. So in this example, we know that a squared is a. Do you remember the name of these kinds of matrices we talked about last time? I didn't formally define it in just a definition box, but I defined this in one problem. Do you remember what was the name of these matrices? If a matrix squared becomes equal to itself, and you yourself trying to give me an example, which is because one possibility is to consider A to be I, but then the question is that is I the only possible answer to this? We saw that no, you gave me an example, it didn't work, and then you fix that if you remember. Okay, so
Was it called an idempotent
yes,
matrix?
it's called an idempotent matrix. And do you remember what was the property of an idempotent matrix?
Was it that you can have as many powers as you want, but it will always be the same?
Yeah, so that is important. So if you have a matrix whose square is equal to itself, not only its square is equal to itself, but any power of it is equal to itself. And we proved this using mathematical induction, if you remember. Okay, anyway, that was just refreshing your memory. I want to wait for you to solve that problem as well. But I think this is also very easy. Okay, do you have any opinion about the next problem? 125. Yes?
Well, I started with left-hand side, and then I rewrote a as, or I went from a to the power of 5 to just simply a.
A, yes.
And then I could write b to the power of 5 as b to the power of 2 to the power of 2 times b.
B.
And then I did a plus, and I expanded that 1b inside the power of 2, and first I showed that it was
Yeah, so let me just try to follow yours. So what you're saying is that because a squared is a, we actually proved, let me see, which problem was that? Where was it? Do you know? Yes, here. This example. A square matrix A is said to be idempotent matrix if A squared is A. Show that if A is an idempotent matrix, A to any power, not just 2, becomes itself. So this is what we actually showed. Okay, now let us go back to the problem here. So what you're saying is that A squared is A. In what I want to prove, I have something related to A5. So let us conclude something for this. And then because of that example I just mentioned, A to power 5 is A. So it's very simple. And what you are also telling about B5 is true. But in your calculation, if I understood it correctly, you need to calculate B squared somehow. So let us calculate B squared first. So B squared means, because B is given to be that expression, so I can write this. Yes? But can I use algebraic identities? Yes, because 2A and I commute. So I can use the algebraic identity. So this becomes the first one squared, 2 times the first one times the second one, which becomes minus 4A, and then plus the second one squared is I. Yes? But then what can I do? A squared is again A, so I can write 4A. Instead of this A squared, I put A in, and then I have minus 4A, and then I have plus I. But this 4A and 4A are cancelled, so what I get is that B squared is just simply I. And then I want to calculate B5, so as Robert mentioned, B5 can be written as B squared to power 2 multiplied by B. But B squared is I, so this becomes I squared times B, and then it becomes I times B, and it becomes B. So we realize that B to the power of 5 is also equal to B. And then it is done, yes, because the left-hand side of that expression is A to the power of 5 plus B to the power of 5. A to the power of 5 is equal to A, so I take it off and replace it with A. And then for the same reason, I take this off and replace it with B. Then I realize that is equal to the right-hand side. Yes? That is also simple. Okay, for the next example, let me ask you one question before you start working on it. I don't know if you have already done that. So forget about this condition. If A and B are numbers, what is the answer to this question bar? Yes? 0. Yes, because if A and B are numbers, there is no difference between these two, okay? But now these are matrices, but not any kind of matrices. A and B are related using this relation. We want to simplify this matrix. A simplification is a little bit subjective, but try to simplify this as much as you can under this condition, okay? So this is what I'm saying. There is no guarantee to answer that this is the 0 matrix, because if they are numbers, the answer is of course 0. But you know that in numbers, you have commutativity, which plays a significant role here. For example, in numbers, there is no difference between BA and AB. But here in matrix algebra, we know that in general, there is no guarantee that BA is equal to AB unless you can prove it in this particular case. Okay, I want to wait a little bit for you so that you can solve that problem yourself. Now, if you have the answer, please tell me what is the simplified version. Then if that's correct, we start discussing your solution. Do you have the answer?
I think it's the 0 matrix.
Okay, so can you defend yourself? I think the answer is correct.
Yes, because we can prove that A times B is equal to B times A, which means that A and B commute.
Oh, okay. So that is the idea. Actually, that's correct. Because this assumption here will help me in this way. So what Alexander is saying is that because of this assumption, I can guarantee that A and B commute. Why is that? So everyone can now participate. Okay, so he's claiming that because of this assumption, I can make sure that AB is equal to BA. Yes, because you have already solved the problem, I asked someone else. Yes?
Oh, okay, so what I did was like, well, I didn't do it completely, but I figured if you replace every single A with 2b squared minus 3y, then the only things you have are B and the identity matrix, and then it would be able to commute.
Yeah, that is probably true. This will work. Yes? But let us try to solve a different problem, okay? So I give you this, and I ask you to show that this matrix that is the answer to this with B, they commute. Let us change the problem a little bit. Because if I can show that they commute, might be I can do it simpler than what you said. In the way that you are saying that we have to expand a little bit. Yes? Okay, so what can I do here? Why they are equal? So let us calculate, yes? I want to see that what is AB. AB, I will take this one instead of A, I put this expression and multiply it by B. But distributivity, I have it, so this becomes 2b squared times b, it becomes b cubed, minus 3i from the left side will be multiplied by b, but it doesn't matter, it becomes b. So if you ask me what AB is, I show you this. Now if I ask you what BA is, I would write B this time, but instead of A, I put this expression. This becomes 2b squared minus 3i. And then I multiply it from the right side, so this becomes 2b cubed again, minus 3b being multiplied by I from the left hand side, but bi is also b, so it becomes minus 3b itself. So this one is equal to that. This one is equal to the same thing. So this means that these two matrices actually commute. So that's also interesting to see that sometimes you can prove these things very easily, okay? Okay, now that A and B commute, then I can expand that expression, yes? Not using this anymore, probably we don't need that. For example, that question mark there is A, yes? And instead of BA, can I write B squared A squared? Yes, and then I can write B. But now A and B also commute, so I can use that formula. So this becomes A squared B squared A. or I don't know, in any way that you like to do it. For example, let me just remind you of some theorems. Can you tell me that, can I commute these two? Yes or no? I know that A and B commute, but this is A squared and B squared. Can I still commute them? That was a theorem, yes? If we have two matrices commuting, any power of one of them will also commute with any power of the other one. So here I can also commute. I'm not saying this is the best way or the only way to answer after that, but this is one way at least. Yes? I commute these two. For the same reason, I can commute the middle one. So this becomes B squared, A squared, A. So I commuted these two. And then, of course, everyone knows that this is A cubed, and this is B cubed, minus this is B cubed, this is A cubed. But for example, I keep A cubed, B cubed the same. For this one, I can still interchange them referring to the same theorem. If A and B commute, A cubed and B cubed also commute, yes? And then everyone sees that this is the same matrices I'm subtracting, so that becomes a zero matrix. From here to here, I am not saying that this is the best way, or if there is any best way. So you can just convince yourself how it works. But I think that was the interesting part here. Any questions? So these kinds of questions in matrices are actually, I would consider them fun problems, yes? Because you are using the ideas, because it makes it more clear for you the differences between the number algebra that you have used so far and the algebra for matrices. Okay? Okay, let us go back to slides now. So I want to start the last part of this matrix powers. So high powers of matrices. So I put it in a different section because sometimes it is important. So if you don't mind, let me just read it to see if I have made any mistakes in my writing. So let me just read it from the text. Even though computing a high power of a square matrix is not complicated from a theoretical point of view, but is tedious and therefore computationally complicated. For example, if A is a square matrix, to compute A to the hundredths, one in principle needs to multiply A by itself 100 times. So it is not complicated thing from theoretical point of view, yes? But this is a costly computation, especially when A is of a high order. Of course, if I have a very big matrix, if I want to raise it to power 100, it's very tedious. During this course, it depends how much we can go forward, we will learn about some special cases that this computation can be done fairly simply. One idea that might be helpful in this regard is to compute the first few small powers of A, okay, to see if one of these small powers of A relates to the identity matrix I or any diagonal matrix, okay? One of these small powers of A relates to the matrix A itself, or there is a general pattern that the entries of the powers of A are following, and use mathematical induction to prove that this pattern is followed by A to the nth in general for every natural number, yes? So these are some strategies, but this is not a systematic way of solving that problem. Systematic way of solving that problem depends in a little bit more advanced topics. Hopefully we can cover it by the end of this course, and that is the notion of an eigenvalues and eigenvectors. So then we can use those ideas to diagonalize a matrix and then try to solve that problem. But for the time being, by the way, this is a good trick to learn about these problems. And there is nothing that I can teach you here unless give you some examples to make you familiar with these 3 points here. We just start calculating some small powers of A that we can calculate by hand or by computer. Of course, computers are very good in calculating even very high powers. But if you want to do it by hand, you calculate several powers of that matrix so that you can either find a relation between some of these powers with the identity matrix or some diagonal matrix, because identity matrices are extremely simple to raise to power. which is of course trivially the identity matrix itself, and the diagonal matrices are also very simple. Or you find some power of n, or power of matrix relates back to the matrix itself. So something like the idea of idempotent. So I mean, if the second power happily becomes, fortunately becomes A itself, then you don't have any problems with high powers. Might be this does not happen in the second one, might be the third one returns back to A itself. But still you can solve something easily, okay? And the final idea is that, is there any general pattern going on between the entries? Because some matrices are like that. So if you start raising them to powers, then you realize there is a pattern going on between the entries of the powers and the entries of the matrix. And then you will have an educated guess about your pattern. But of course, this is not mathematically proven yet. You can use mathematical induction to prove that your guess is indeed correct. So let us try to solve these problems together. So determine A to power 41 if A is this square matrix. Okay, so we want to apply the rules that I mentioned here. I think you can start, by the way, seeing that. These problems are a little bit more advanced, this one and that one. We will come back to that later. But I think in these three examples, I already mentioned what are the ideas. Okay, so it doesn't matter. You can spend time on working on them as far as I'm just cleaning the board here. Okay, could you solve the first one? Wasn't it clear? Okay, might be. Hopefully I haven't done any mistakes in typing them. So because, let me try to do the first one at least. Have I written it correctly? No. Did you take this from me or no? From the slides? There's a difference here. But I don't know, the first few minutes, probably you could see the slide. I wrote it slightly later than you. Anyway, so this is the correct one, if I haven't done something wrong. Okay, so let us check. This matrix is given. I'm supposed to calculate A to power 41. So what should I do? The first thing that I do, I will start calculating the low powers. So A squared means matrix A, which is -2, and 2 and 0, multiplied by the matrix itself. So it's -2, 2 and 0. So what do you get? So this row should be multiplied here. This becomes +4, -4 becomes 0. This becomes +4, 0, so it's +4. And then this becomes -4. And then this becomes -4. Did you get the same thing? Yes? So this A is squared. It's still, there is no hope that we can solve the problem. So let me just be patient and calculate the next one. The next one, for example, I can interpret it as A squared times A, or you can interpret it as A times A squared, even though it is important, but we realize it doesn't matter for powers of one single matrix. So A squared is that matrix, 0, 4, -4, and -4, and then I multiply it by -2, -2, and 2 and 0. I don't know, hopefully this will work. So this one times that one, what's the answer? 0, 4 is 8. This one, that one is 0. This one is +8, -8, okay, 0. And then that becomes +8. So this will work actually. Yes. So the third power of my matrix somehow is related to the identity matrix. Because this is not identity, but it is 8 times the identity matrix. So I can write it as 8 times 1, 0, 0, 1, which means it is 8 times the identity matrix 2 by 2. So the third power related itself to the identity matrix. So it was not time consuming, yes? But I was lucky, so I have to engineer the entries in a way that it works, because we are not solving it systematically. Okay, so what we are doing, we want to calculate A to power 41. So then what we are supposed to do? Try to write this, yes?
Maybe you can take A to the power of 3 to the power of
13, yes, because my question mark is a to the power of 41. I realize that something good is going on about a to the power 3, so this motivates me to write this, if possible, in terms of a3 as much as I can. So then it means that, okay, that's not hard, because I can write it a to the power 3, and I want to reach to this exponent, so it is clear that I multiply it by 13, it becomes 39, but it is not still enough. I have to compensate for that by multiplying it by an extra a to the power of 2. But instead of a to the power of 13, I can put that expression in. So this becomes equal to 8i to power 13. And instead of a squared, I have it on board. It is 0, 4, minus 4, and minus 4. Yes? But then 8 to power 13, I don't know. I don't need to know. I just write a to the power of 13. But the important thing is that the matrix involved is not complicated anymore, because I to power 13 is just I, and I multiplied by any matrix is the matrix itself. So this becomes multiplied by 0, 4, minus 4, and minus 4. If you want to write it a little bit better, what can I do? I can write this as a power of 2, so it becomes 2 to power 39, and all of these entries are 2 to power 2, and then I multiply it in, but I cannot make it very simple because this number is a huge number. So then it becomes 0. This is 2 to power 39 times 2 to power 2, so this becomes 2 to power 41, and then this becomes minus 2 to power 41, and then minus 2 to power 41. So that was interesting. So that was the answer actually. Yes. So when I raise this matrix to power 41, it turns out to be that matrix. And by the way, I don't know how GeoGebra reacts here because this number is huge. So let us go here and see how we can calculate matrices using GeoGebra. So the first thing that I do is just go into this manual. So you can just check it yourself how to put matrices in GeoGebra, and then how calculate things using, for example, matrix operation. So addition, subtraction is the same. If you want to multiply a matrix by a number, so you have to use this asterisk, and then the same thing for matrix multiplication. Later we will also learn they have also matrix division, which is a little bit different. So they have defined what they mean by this. We haven't studied that yet, but then we will also probably hopefully study about matrix inverses. Okay, so let us now go to GeoGebra to see if we can do it here. So according to that one, so I just open curly brackets and I type them. So another curly bracket is needed. So it's minus 2 and minus 2. So this is the first row of my matrix. And then I go and type the next row by putting it in curly brackets again. So it is 2 and 0. Okay, so I don't know if I press enter. Oh, okay. So it gives me this matrix. And the point is now I want to see that, because let us see how it works. M1 to power 41. I just type it to see. Yeah, it works, but that number is a huge number. We can check that that is correct. So let me open up this. I hope that it can write it in the matrix form. Yes. So this is the number we get. This is the matrix we get. And if I calculate that number, 2 to power 41, and that's the same number. So you see that here, yes, so we were able to actually calculate the matrix to power 41. So this number that you see here is exactly 2 to the power of 41, but of course you couldn't expect me to be able to calculate this. And that is enough, by the way. Okay, so we were able to calculate this. Okay, let us go back to the board and try to consider the other one. So could you solve the other one? Yes, so again, so you see fairly high powers, so you need to remind yourself, this is the only trick that you know, 3 tricks. The first one was the example for the case that some small power of my matrix is somehow related to the identity matrix. Okay, so let us calculate this one. What is your opinion about this second one? So let us calculate a squared. I think this is simple to see probably the pattern, yes? Because if I take this 1, 1, 1, 2, 2, 2, and 3, 3, 3, and I multiply it by itself, 1, 1, 1, 2, 2, 2, and 3, 3, and 3. Let us see how it goes. So this is multiplied here. So what's the answer? So this row multiplied by the first column gives me what? No, one answer. I want to write something here. 6. Because 1 times 1 is 1, keep it in your head. 2 times 1 is 2. 3 times 1 is 3. 1 plus 2 plus 3 is 6. This is 6. But I hope that you immediately see what's happening next. Because I will take the same row, but multiply it here. But every time 1 is multiplied by 2, 2 is multiplied by 2, 3 is multiplied by 2. In the previous case, every one of these numbers are being multiplied by 1, but this time every one of these numbers is being multiplied by 2. So it is clear when I add them, the result will be 2 times the previous one. You can check it. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. If I add them, it becomes 12. And then I hope that you immediately guess what will happen for the next one even before calculation, because that is the same thing, but I'm multiplying it by 3, 3, and 3 this time. So it becomes how much? 18. And then it is very clear, by the way, I really don't need to bother about multiplying the other one. So what will happen then? It becomes 6, 12, and 18. 6, 12, and 18, because that's the same row. These are the same rows, so when I multiply them, it will generate the same numbers. Okay, but then what can I do now? I can factor a 6 out, for example. Yes, if I factor a 6 out, I have to factor it from all entries. Remember, when you want to multiply a number by a matrix, you have to multiply it into every entry. So when I factor it out, I have to factor it from all entries. So this becomes 1, this becomes 2, 3, 1, 2, 3, 1, 2, 3. Yes? But if I ask you what this is the same matrix itself. So what I realized that the second power is 6a. So then I don't know, do you have any idea? But this is unfortunately not idempotent because this is 6a. Yes?
Maybe if you prove it using induction.
Proving induction, you need to have a pattern. Yes?
Okay, well, I think the pattern is 6 to the power of n minus 1 times a is the same as...
Yeah, I think that's correct. Either you can go for it, or because they are not asking you for a general power and the power is not that big, might be we can just raise it to some power 2. That's also possible. So I can raise it to power 2, it becomes 4, this becomes 36a squared, but a squared is 6a, so this becomes what? 216a itself. Yeah, might be your idea is better if you can prove it. So what you are suggesting is that we can prove that a to power n is 6 to power n minus 1a. So this is your guess. Yes? Okay, that's also good. Yeah, we can prove this idea. And then we replace it with 19, so this becomes 6 to power 18 times a, and that's also what we get. So let us prove it by mathematical induction. So how can I do that? Of course, for n equals to 1, that is correct, because the left-hand side becomes a, this becomes 6 to power 0, 1 times a. So if I call this Pn, P1 is actually a is equal to 6 to power 0a, which is true. And then we assume that this is true for k, meaning that a to power k is 6 to power k minus 1 times a, assumed to be true. We want to prove that this is also true for this case, so we want to prove this is the case. Yes? So this is the question mark we want to show. This we know that this is true. So this is also very simple. So I start from the left-hand side, which is a to power k plus 1, and then this becomes a to power k times a. Yes? a to power k is 6 to power k times a, and then you multiply it by another a. No, I made a mistake, yes. A to power k is 6 to power k minus 1. Sorry, a to power k is 6 to power k minus 1 times a, another a. And then this becomes 6 to power k minus 1 a squared, but a squared itself is 6 times a, so this becomes 6 to power k minus 1 times 6 times a, and then what happens, this becomes 6 to power k times a.
There's someone knocking on the door.
Yes, I will go. So this becomes the right-hand side. We prove it. Okay, so in that case, if I want to calculate a to power 19, then the answer will become 6 to power 18 times a. But of course, if you want to write it officially, you have to take this number and multiply it here with the matrix. So that one I will pass. So that is also possible. Yes? Okay, now we go to the next one. The next one is this one. Could you solve that one? A to power 100 was wanted. Let me check that if I have done something wrong or that is exactly what we have. Yes, we want to 2 minus 1, 1, and 0. So let us calculate. Yes, because there's not time that much left. So here, if I ask you to calculate a to power 100, the first thing comes to mind is to start calculating some low powers, yes, of a. So we start with a squared, so it is 2 minus 1, 1 and 0. 2 minus 1, 1 and 0. So what happens here? If you multiply that, so you take that through and multiply it here, what the answer is, it's 4 minus 1, 3. And then you do the same thing here, it's minus 2. And you do the same thing here, it is 2. And then you do the same thing here, it's minus 1. Did I do it correctly? 4 minus 1, 3, minus 2, 0, that's correct. 2 plus 0 is 2, and then minus 1, that is correct. But apparently it doesn't seem very promising now. Yes, do you see any idea? But let's calculate the next one. So the next one might reveal some kind of pattern, I don't know. So this I can interpret it as a times a squared or a squared times a, it doesn't matter for this case. So then I will take 3 minus 2, 2 minus 1, and then multiply it once more by my original matrix, which is 2 minus 1, 1, 0. And then you take this one and multiply it here. What happens? It becomes 6, it becomes minus 2, so it is 4 now. And then you multiply this there, it's minus 3, because this one is 0. And then you multiply this one 4, multiply this one here minus 1, 4 minus 1 is 3. I think that some pattern is revealing itself now. Yes, 2 times minus 1 is minus 2. So a to power 1 was the same, this matrix. A to power 2 becomes that matrix. A to power 3 becomes this matrix. I'm not saying might be, you can see a pattern. And even if you see the pattern, there is no guarantee that this pattern continues unless you can prove that pattern is working for all possible values. Can you see the pattern? Yes? A to power n, so can you tell me what is your guess? So guess.
I'm guessing that maybe it's
A to power n is equal to
well the opposite diagonal. If that's both of those are just multiplied by n.
it seems so, yes, because the original matrix A here has minus 1 and 1. Then the second power became minus 2 and 2. and the third power becomes minus 3 and 3. At least this is an educated guess to say that, okay, for a to power n is minus n here and n here. Okay, there are two more entries we need to guess. So let us check this entry. If it is 1, this is 2. If it is 2, this is 3. If it's 3, this is 4. So probably if it is n, it would be n plus 1. Yes? This is apparently the case. And then here, if it is 1, this entry is 0. If it is 2, this entry is negative 1. If it is 3, this entry is negative 2. So can you tell me if this is going to follow this pattern? If this is the n number n, what will I expect here? First of all, I need to have a negative sign. But the value is 1 unit less than the power. Yes? So if the power is n, so I should write n minus 1 here. Yes? So this is the pattern that apparently reveals itself. Or if you don't mind to multiply this minus sign in, it becomes 1 minus n. So let me clean this. It is easier to work with 1 minus n version rather than that. So that is our guess. So, and then we have to prove it. So this guess, even though it is correct, this is not complete from a mathematical point of view. You have to consider this, for example, let me give this a name P of n, and then try to prove it using mathematical induction. But because you have enough experience in mathematical induction, I want to wait a little bit more so that you can practice it here again. So prove that this is valid using mathematical induction. I pause recording, waiting for you. Okay, did it work? Okay, so let me just do it for you. So if you first you need to see if p of 1 is true. Of course it is true because we guessed it based on that. So a to power 1 is, I replace n with 1 everywhere. So this becomes 2 minus 1, 1, and 0, which is true. Now I assume that this is true for k. So I mean that a to power k is indeed equal to k plus 1, and then minus k, and then k, 1 minus k. This is assumed to be true. And then I have to prove that this is also true for the next number, a to power k plus 1. I want to prove that. Okay, wherever I see n, I have to replace it with k plus 1. That becomes k plus 2. But then remember, this becomes k plus 1 because of the negative sign, it becomes minus k minus 1. Yes, I'm replacing k with k plus 1, but this minus sign goes for both of them. This becomes k plus 1. And then if you do that one here, minus 1, I replace k with k plus 1. If I apply the minus sign in, this one and that one are gone. So this is what I want to prove. Yes. And then, of course, you know what to do. Yes, you want to start, for example, from the left-hand side, and then somehow you want to do something that you can use this. And that is very easy because a to power k plus 1 can be written as a to power k times a. If you have written the other way around, it doesn't matter because any powers of the same matrix commute. So for a to power k, I can use my assumption, which is k plus 1 minus k divided, by k and then 1 minus k. This is a to power k. I have to multiply it by a itself. So a itself is this matrix. So it is 2 minus 1, 1, and 0. And then do the matrix multiplication here. So I will take this row and multiply it here. So 2 should be multiplied by the first entry. Minus k should be multiplied by 1 and then added together. So that becomes the first entry of the product. And then I will take that one and multiply it here. So minus 1 should be multiplied here. So it becomes minus k minus 1. And then minus k multiplied by 0, it is just 0. And then here, 2 times k. And then I have to multiply 1 by this and add it to the previous. So this becomes 1 minus k. And then this goes here, it minus k. This is 0, so it's minus k. And just a very minor simplification. So if I multiply 2k and then there is a minus k here, I am left with k, and 2 times 1 is just 2. That is nothing that I can simplify. The 2k minus k is k, and then I have a plus 1, and then I have minus k. Hopefully you compare, yes, that's correct. That is exactly what I wanted, so that becomes the right-hand side. So this proves exactly that my guess is correct, but my goal is to calculate a to power 100. I raised that, but that was the point. So you want to calculate a to power 100, so a to power 100 becomes equal, I replace n with 100. By the way, that is also interesting to see that in this case, this does not become a matrix with huge entries. Yes, even though the power is much bigger. Yes?
It's 100, not 101.
Oh, yes, minus 100, thank you. And then this is 100, this is minus 99. So you see, even though the power is much bigger than the previous one, do you remember a to power 41? It becomes more or less a huge matrix, huge in respect of the entries. But here it's not very big one. A to power 100 is this matrix. It's also good to check it with this GeoGebra. So let us see how GeoGebra works here to improve our experiences. So here, if I define another matrix, so what was my original matrix? It was 2 minus 1. So it is list of lists. Yes, so that is very common for programs. Yeah, to use list of lists for matrices. So here what I have, what 1 and 0. Okay, so that is another matrix. So now I want to raise M3 to power 100. Yes, to power 100 and see what happens. So it's 101 minus 100, 100 minus 99. That's correct. So, but of course for computers it doesn't matter. They can calculate these things very fast. And that is, by the way, one of the reasons that linear algebra is extremely powerful, because the machines can understand this language very, very good. So if you can reduce the problem that you are solving and try to write it in terms of matrices, then that is a actually good starting point to solve the problems using computers. Okay, so here I actually want to stop here. So what I get is this. I will get it here. Let me go back to the notes. I want to keep these two problems for you, and I will start from these two examples next time, okay? They are more technical, so I mean, the idea is still, oh, by the way, I forgot to write 2023. When I was writing these notes for the first time, it was 2022, okay? But it doesn't matter. You will see that the reason, if you understand how to solve the problem, then you will see it doesn't matter how big the power is here. And this is also from theoretical point of view an important problem. Yes? So I want you to think about this. Next time I will start from here, but what I wanted to talk about matrix powers is finished here. So next time, after solving these two problems together, I will actually switch to a new topic. Yes? So I want to talk a little bit about special matrices. Yes. And I haven't added some problems yet that much, but I will add some other problems here. But I don't know how many of you have started working on the previous problems, because there are many problems involved from the previous cases. Yes, where are they? Yes, before this. So there are also some good problems. If you haven't worked on these problems, I recommend you actually pick some of them and try to work on them. If you have any questions regarding them, we can also talk about those as well. Okay, any questions? Okay.